So our next speaker is Brian Lockman. He's going to talk about simulations of self-acceleration dynamics.
Cool. Can you all hear me well? I'm kind of taller than the microphone. Okay, cool. So I'm here today to talk about characteristics of self-acceleration-driven gravity wave instabilities. I've been working on this at GATS with Dave and with Tom Lund at NWRA. And today's workshop is 50 years of gravity wave research, a tribute to Colin Hines. And I think it's really appropriate this is being done at CEDAR. I mean, gravity waves have definitely proven themselves to be an incredible coupling mechanism between the troposphere with orographic generation, momentum and energy deposition within the stratosphere and higher, and even tickling the ionosphere and having effects there. So, and again, thank you for giving me the chance to speak here today. Just a quick outline. I'm going to talk briefly about what self-acceleration is, show you an example of that. From there, I'm going to talk about our current modeling efforts, and then the meat of the talk, a bunch of different results detailing self-acceleration braking and its dependence on the input forcing, and then we'll conclude with the obvious conclusion. All right, so over the past couple of days, I tried to come up with an analogy for what self-acceleration is, and I really haven't succeeded. So, you know, if you stand in a bucket, you can't pick yourself up, but if you're a propagating gravity wave, you can accelerate yourself. Self-acceleration is basically an interaction mechanism between a propagating gravity wave and the background flow in which it propagates. There's a couple other mechanisms, right? There's wave braking. So a gravity wave propagates up, the amplitude grows, it breaks and deposits its momentum to the mean flow, accelerating it. There's viscous coupling. You can have a wave propagate and viscosity accelerates the mean flow without leading to wave braking. Self-acceleration is simply another mechanism by which the background accelerates. What happens is you have a wave packet, denoted here, and it's got a momentum flux associated with it, and this is propagating to the left. And because it has a momentum flux divergence in the leading edge, it accelerates the mean flow. This is a conservative and transient effect, though. As the wave packet propagates up, you have a similar effect on the back end, and the mean flow restores to its previous value. Yeah, and this is just an example of what happens when you allow the mean to evolve due to the packet passing. Specifically what happens is the following movie. So what's going to happen is this wave packet is going to propagate up. The velocity deficit to the mean flow is going to increase with altitude since the density is decreasing. Once this attains a large enough amplitude, it can actually accelerate the phase lines of the wave itself, causing them to kink and ultimately break. And this is normalized by the peak amplitude because it gets quite large. So, and just kind of to watch it again because it's awesome. So it's got this linear phase where it simply vertically propagates. And again, you can see this is conservative. Once the amplitude gets large enough, you can see the phase lines kink as this gets large. And then it goes unstable and breaks, and then the momentum flux begins to deposit itself into the mean. So. This contrasts with the case where the mean wind is fixed and the wave simply propagates through without altering the environment. And here you get the more traditional convective overturning as the amplitude grows. So this is 0 to emphasize the fact there's no mean wind deficit. So your wave propagate ups. The amplitude increases, it goes unstable, and the momentum flux dissipates. So modeling efforts, all the results presented in this talk are derived from the inelastic Navier-Stokes model that we've been using. It doesn't allow for sound waves, but it is compressible, so it takes into account density effects, which is pretty important to this. I mean, you need the amplitude growth with altitude. The current results, all the runs in this talk are done in an isothermal atmosphere, so they're slightly non-physical. Smaller waves can get higher than they could in the real atmosphere. All the runs are initialized with a headwind just to keep the camera basically fixed on the wave. But the wind is vertically, has the same value. All the runs are initialized with a 2D wave packet that's periodic in the horizontal and infinite in the horizontal and confined in the vertical. And then for the 3D ones that we do, we seed it with a little bit of noise to instigate the span-wise instability. All right, so the first thing to talk about is sort of the instability character of self-acceleration braking. So here you've got your sort of linear phase. this is the vorticity magnitude field. And you can see that as the background wind increases, it starts to kink the phase lines, and they go unstable. These times are in buoyancy periods. You can see there's a pretty large jump between these two time steps, and it isn't until 14.8 buoyancy periods that the span-wise instability really kicks on. So self-acceleration braking really seems to be a fundamentally 2D process, and that's kind of nice because when you want to model it, you can throw resolution at the streamwise scale without having to worry too much about the span-wise. When you start to do the turbulence modeling, you obviously have to go to 2.5 or 3D. And this contrasts with the fixed mean case where you've got your wave propagate up, the amplitude grow, and then you have convective braking. Here the instability kicks on around 13.4 or 13.5 buoyancy periods, and you can see in the span-wise direction you're beginning to get your streamwise aligned rolls kicking up. So yeah. And then, since I'm really just kind of showing you what we've seen so far with the self-acceleration braking, these are just 4 fields that characterize the braking. So you've got your horizontal velocity perturbation, your vertical velocity, your potential temperature perturbation, and then vorticity magnitude. And kind of depending on what you want to look at or diagnose, they all have different value. We tend to look at this a lot just because it highlights the small-scale structures very well. But you can see in all of these the effect that the mean wind has, where it kinks the phase structure, accelerating it, and then leading to the instability. All right, so we wanted to look at different effects on the dynamics to see, what was going on. The first thing we considered was viscous effects. In an isothermal atmosphere where your density decreases with height and you've got no variation in the mean wind, this corresponds to basically changing your initial packet height. So this simulation with a higher viscosity was initialized at 60 kilometers. This on the right was initialized at 10. They were allowed to propagate up, and they break at roughly the same altitude. This gets to about 130. This gets to about 81, so a difference of 49 instead of 50. So one potential impact of the viscosity is to slightly retard the altitude there. Other than that, if you look at the velocity fields and even the vorticity fields, they look pretty similar. The only real difference is that the smaller scale structures here are wiped out when you increase the viscosity, which you kind of expect and is consistent with how viscosity behaves. The second effect we looked at was the initial frequency of the wave, and so we ran 4 different cases with different frequencies: n over root 2, n over 2, n over 3, and n over 4. These all have the same non-dimensional amplitude, where the amplitude is u prime over the horizontal phase speed. Those phase speeds are given in the appropriate panel. And what's interesting about the frequency dependence is that it affects the altitude at which these things break, but they all appear very dynamically similar. They all have a similar looking phase kink and structure. And so this kind of leads us to wonder, if there's a dispersive effect going on here where the lower frequency waves, the leading edge of this is running up, growing in amplitude, and then breaking, leaving sort of the lower frequency component behind. We're not fully done diagnosing this, but it does appear fairly compelling. Related to that, we looked at amplitude effects. So in each of these cases, we initialized it with a wave packet of differing amplitudes, and sort of as you expect, if you decrease the amplitude, the braking happens higher up. You have some critical amplitude at which you'll have this self-acceleration happen, and so if you reduce your amplitude, you have to go farther up to grow larger. So yeah. And again, the shape is pretty consistent across all the panels and propagation times. So the nice thing about this is, you have a wave propagate, the amplitude grows with altitude. According to this kind of common relationship. For the wave I just showed you, it's pretty easy. If you want to dial in and have your braking happen at some target altitude, you pick the appropriate relative amplitude, let it go, and it works. It turns out that while it works for the n over root 2 case, the very fast case, for n over 2 and n over 3, it doesn't really obey this relationship. This is an example of 3 different n over 3 waves. The black line is the target, based on this expression, and the white line is where it actually breaks. And it turns out for the n over 2 case, this coefficient 2 here is actually about 2.5, and for the n over 3 case, it's about 4.6. And I do want to offer a word of caution. These are still sort of preliminary values, still trying to figure out exactly what the relationship is and how well defined it is. The last thing I want to talk about is the dependence of the braking on the horizontal length scale, and this does seem to have an effect. This is the 20-kilometer wave, similar to the other panels that I showed you. When you cut it in half, the region of braking goes down by roughly a factor of 2, and when you double it, it increases by a factor of 2. There's a little bit of difference here in the apparent dynamics, but the same general shape holds true. The other thing to note is that this occurs at about twice as early as this, which occurs earlier than that, and that's just an incidental consequence of the fact that the longer waves have a larger vertical group velocity. So, and then the last movie I wanted to show you, since it does seem to be this leading edge, which is important, and in this isothermal atmosphere, it can basically go as high as it wants. We have a case where there's actually 2 incidences of self-acceleration from just one initial wave. So it has a fairly modest amplitude. So it propagates a little bit. The mean grows and accelerates the wave field, begins to kink, and breaks. But there's still this leading edge, which continues to propagate vertically and impact the flow and break again. So, and I'll show it again because I like it. And again, self-acceleration is more or less a 2D instability. So while the turbulence dynamics down here might not be completely right, I think you can definitely trust this result. So I don't know how long that was, so I definitely came in under time. Conclusions and future work. So the first thing I'd like to point out is that, self-acceleration seems to be a very natural consequence of vertical wave propagation. Gravity waves have momentum flux associated with them, and as they increase in altitude, their amplitude grows and they impact the mean flow. They also seem to be a very effective instability mechanism. If it grows large enough, you're going to have your phase lines kink, go unstable, and break. It does appear that the dynamic signature of these events is largely determined by the horizontal wavelength. They don't seem to depend on the amplitude or the frequency or viscous effects. This isn't to say that's the only thing that determines their character. There's other things to look at. The background clearly is not going to be isothermal in the atmosphere, and it could be that the value of the stability changes it, that ducting structures change it, that shears it might encounter would change it, but that it would still be fundamentally a self-acceleration event. Future work that we're looking at is to, again, fully characterize the potential role of dispersion. We think that's what's going on, but it remains to be fully fleshed out. And it's also a future goal to parameterize a relationship between the sources and events. What amplitude gravity wave do you have forced by some feature, and will that lead to self-acceleration at what altitude? Additional things to consider, again, realistic background environments, since that's the ultimate long-term goal, to hook up with observation. One of the other goals of the future research is to localize the forcing in the streamwise direction. Again, you don't really have many infinite gravity waves launched. And so that's definitely on the table. And then to look in 3D at localizing it in the spanwise as well as the streamwise to see if sort of the spreading of the gravity wave reduces the ability to accelerate the mean flow enough to lead to braking or not. And then the last bit of future work is to compare with observation. And I like to say the future is now, because at the end of today's session, I think Mike Taylor is going to get up and show observations of what could potentially be examples of self-acceleration and braking. So that's my talk.
Most of your plots went up to 140 kilometers, but it looked like your simulation might have gone much higher. And I was wondering what percentage effects you might have at 250, 300 kilometers altitude.
So there's 2 things to say about that. First of all, since these are idealized, they can totally get that high. Basically, that just gives you more room to kind of play with. So, if you reduce the amplitude of your seed wave, then they can get that high. And basically what you do see is a lot of this kind of continuous braking where this little lead edge keeps growing in altitude and breaking again, and then its lead edge continues up and breaks again. As far as the real atmosphere, getting up to 260 kilometers, I'm not sure that's, I mean, that's kind of speculation, right? Because you're going to encounter changes in background temperature and wind, which are probably going to confine that ongoing propagation, cause it to break or deposit. So I will also say that getting that high in the model resolution starts to kill our time step. So
Doesn't mean the gravity waves can't get there, though.
no, definitely not.
William?
I was curious when you, of course, simulating and using data validation is important. So how would you envision doing that? Would you set it up with a case study with Mike's data, or do you have cases that you could simulate, or how would you proceed to do that?
At this point, I think the goal would be to kind of just look through the data that LiDAR is always running, ergo observations are always being made, to basically look through that and see something that has a signal that matches one of these. And then if you do find something that looks tantalizingly close, you could set up a more realistic simulation using the observed temperature and wind data and run a simulation there to see if it agrees. But I think the first step would basically be just to make observations and see something that looks kind of right.
Thanks, Gray. William, did you have something?
Yeah, I just wanted to query the whether you've considered, in terms of realistic profiles, tidal variations.
We've begun to look at tidal variations. Actually, on this very first slide, this is done with a 120 kilometer wave in the presence of a background wind. And this one actually kind of undergoes similar convective wave breaking. There are some other cases around with a wind where it's able to penetrate and then break. I've also done some simulations with isolated thermal ducts, and when you let the mean evolve versus keeping it fixed, you do see a difference in the dynamics. So I'm not entirely sure that's just straight up self-acceleration, but it does appear to have an effect even in non-simple atmospheres. But we haven't done a lot of work with that yet.
Yeah, I mean, it may be an obvious question, or already answered, but I've always wondered whether the gravity wave effects with a tide and without a tide are significantly different, and you might be able to explore something like that.
Yeah, I mean, that's, yeah.
Yeah, you're right to be suspicious that that's the case, I think. Thank you very much, Brian.
Yeah, thanks.
But the comment I want to make refers to the remark made by the speaker that we don't have infinitely long gravity waves. I'd like to bring to the attention of all students now the photograph of non-lucent cloud waves made by George WITT back in 1960 or thereabouts. Anyone who hasn't seen those photographs would be well advised to look them up, and you'll find the wave structure at non-lucent cloud heights shown beautifully, including what looks almost like an infinite front. But they're beautiful photographs, and I think there's probably a lot more scientific information in them than has been made use of yet. Thanks.
Thank you, Colin, and I think you're exactly right. There are lots of details that you can see in noctilucent clouds that give us nice insights into these multi-scale dynamics.